Yeah, today we are going to move into our unit on confidence intervals. This is into the inferential part of statistics where we have collected the data using random samples and random methods, whether we use a simulation, an experiment, or some sort of survey. We process the data, and now we want to say, what does this data tell us about? What can we use this for? What sort of inferences can we make based on the data that we've collected? And so we start that conversation by talking about sampling distribution models. And in this case, we are going to be talking about sampling distribution models for means. Remember when we have a population, we use the Greek symbol mu for a mean, and when we have a sample, we use x bar. Just a reminder. So we have talked about distributions now for quite a while, and one of the special distributions we talked about was the normal distribution, or the normal model. It's just a distribution, and mine's terrible when I draw it, but that's okay. You should get used to sketching it, and it's good to help you. And that distribution was symmetric on both sides, and we talked about that the majority of the data points on this distribution were between 3 standard deviations to the left and 3 standard deviations to the right. And we used that to find some probabilities, and we also used probabilities to reverse engineer data points. But those data points on the normal model we've been talking about were just that. They were just individual data points. And so now we are going to talk about data points on a normal model that aren't just individuals, but they're whole samples, and in this case, sample means. So we have this central limit theorem. If you take in calculus, or you're going to take calculus, there's a thing called the fundamental theorem of calculus. I don't remember what it is. It's been a long time. But we have our fundamental theorem of statistics called the central limit theorem. And so if we take a random sample of anything, let's say we want to find a random sample of students in this building, and then we find an average about some characteristic we're interested in, let's say an average height. So we find the average height of a random sample of students in this building, and we document that. And then we find another random sample of students in this building and find their average height. And then we continue doing this process by which we're sampling the same number of students randomly, finding their average height, documenting it, and then we keep finding an average height for the same sample size, different students for different samples, and we put all those sample average heights onto a distribution. It's going to be approximately normal. That means it's going to be symmetric, it's going to be unimodal, and it's going to look like that thing that I can't draw very well, like that. So, and as our sample gets larger, remember sample size is n, as our sample size gets larger, uh, the more normal, or the closer to the normal model uh, our distribution will look. And so, like I said, sample size is n. When we find the mean of that sample, it's x bar. And usually when we find the standard deviation, so standard deviation sigma, that's for a population. For a sample, we would call it S. But in this case, we're going to need a standard deviation of sample means, and so we have this special way to calculate the standard deviation for our sampling distribution for means. And so in notation, we have a approximately normal distribution with a mean and standard deviation. And this is just another place where I'm saying as long as the sample size is large enough, what is large enough? We'll talk about that. As long as it's large enough, then if we keep collecting samples of the same size, these samples have to be from the same size, and we take the sample means and we put them on a distribution, that distribution will approximate the normal model. And that's a really awesome fact because it's going to allow us to find some probabilities as we go. We have some conditions that we need to satisfy in order to use this central limit theorem. The first condition is that our sample needs to have been acquired through random sampling methods. We always need to sample randomly and try to avoid the pitfalls of a biased sample. So we need to make sure that we're sampling properly and we have a random sample. And so when we're trying to use the central limit theorem, we need to document that we've satisfied these assumptions and conditions. This is going to be a practice we're going to use throughout the rest of the year. And so you should get used to writing out and documenting and explaining that we've met the criteria to move forward and use the central limit theorem to answer whatever question it is we've been asked. We also need the individuals in our sample to be independent from each other. And we talked about this idea a little bit, that sometimes independence doesn't exist. So if I were to select a cereal box off a shelf and buy it, and I'm looking for the prize inside, technically I've reduced the number of cereal boxes on the shelves, and therefore I've reduced the probability of getting that prize. However, if we're sampling less than 10% of our population, the effect on the probability will be unnoticed. It'll be so small that it won't matter. And so when we get a sample size, we want it to be large enough, but we also want it to be less than 10% of our population to ensure that we have independent samples. And the last thing we want to make sure, is this normal model going to be totally appropriate? We have to have a large enough sample size. We go with this sort of rule of 30. If we have a sample that's 30 or greater, as long as it's less than 10% of our population, that seems to be sufficient from past research to say that our sampling distribution will approximate a normal model. So let's use this in practice and do a problem together. So pause here, take a second and read this, and then we will talk about what it is we can do with it. So here we have some information about the ACT test in Ohio, taken in 2003, so a long, long time ago. They've given us an average of 21.4. That's for all the students who took it, so that is a population mean. And then they've given us a standard deviation of 1.05 of all the students who took it, so that's sigma. And then they're going to say, okay, if I randomly sampled 25 of these students, so that is n. So I'm going to come down here and actually document that n is 25, population mean is 21.4, standard deviation is 1.05. So we want to randomly sample 25 of these ACT takers, and we want to know the probability that the average composite score is 22 or more. So we now know the probability that x bar from our sample, 22 or more means greater than or equal to 22. And so let's check our conditions that we talked about before. And for time's sake, in this lesson, I will sort of shorthand this, but I will go over and over again. You should write these things out completely. So we are looking for randomness, we are looking for independence, and we are looking to make sure that the normal model is appropriate. And so we've been told that we have a random sample, and so if I were to do this in a formal setting like a test, I would say, or in your practice, you should do this in practice. I would say that the 25 students were sampled randomly. Check. I believe that of all the people who took the ACT in Ohio, the entire state, 25 students should be less than 10% of the population. Also, one student's score should be independent of another student score. They're working individually. Um, they're not helping each other. So we should say that the scores on the ACT are independent of each other. And then we want a good enough sample size. 25 is not 30, but it's pretty close. Um, there's some play here. We would say that if we were to be able to look at the distribution of scores, the closer they are to being symmetric, the more likely our sample size is good enough. This is a little bit of a gray area, but 25 is a good sample size, so we can say that yeah, we're good to go here. And again, you would write this out in sentences explaining that we have a random sample. The individuals should be independent from each other, and the sample size, while not being equal to 30, is pretty large at 25 students. And so I'm going to sketch what this might look like. It's just a sketch. I don't claim to be very good at it. So we should, since we've satisfied all these conditions, be able to use the idea of the central limit theorem. That means if we keep sampling 25 students and finding their average composite score and putting them on a distribution, it should be approximately normal, where the mean is the population mean, and the standard deviation, so the standard deviation of our distribution of means is our population standard deviation divided by the square root of our sample size. So we have a normal model with mean of our population mean, standard deviation of sigma over the square root of n. So there's our population mean, 21.4, average composite score. That means we took all the students in the entire state and averaged their score. Our standard deviation is 1.05 from all the students in Ohio, and we're sampling 25. So the difference between the mean for all the individual students and the mean of this distribution is that we are saying now that this is the average composite if we get a sample of 25. And so the standard deviation is the standard deviation of samples size 25 when we find the average of them. And so now we can use some idea that we used in the past. We want to know the probability that our average of 25 students composite scores is greater than or equal to 22. So 22 is going to be somewhere over here. I don't know exactly where. Greater than is going to be to the right. And so I can go on my calculator. I can hit second vars, normal CDF. My lower is that 22. My upper is 1e to the 99. Basically infinity. It's going to keep going and going and going. My mean is 21.4. My standard deviation is that standard deviation we just calculated. The population standard deviation divided by the square root of the sample size. So 0.21. And one thing we might want to write down is all this information that you see here in the calculator. So there are left bound, our upper bound, our mean, our standard deviation. So you're telling me, hey, I know how to put this in the calculator. And we get 0.002. I'll say 0.0021. So the probability that we randomly select 25 students and get an average score of 22 or higher is very, very small, 0.0021. So less than a 1% chance that that would be the average score. So that was kind of a lot. So if you're working through this problem and you need help, you should definitely ask for it. I'm going to ask you some questions based on this scenario about snakes. If you need help while you're working through it, please do ask. Take the time on these, and then there's more practice on Canvas for you to reinforce this idea.